First, of course, as always, when you go log into your Hawk system, which I've already done over here, just want to remind you of what is due this Saturday and this Sunday. This Saturday is due quiz number 2. Again, you got 2 attempts on this thing, so don't mess it up. It is on section 2.1A and 2.1B, pretty much 2.1, who are we kidding ourselves? And so focus on that particular material and stuff, and chapter 2.1. And I pushed back the 2.1B, so now that homework set is actually due on Sunday, as well as 2.1A and 2.2A and 2.2B. And the instantaneous rate of change is actually what I'm going to be finishing up today, so we're looking at that. So, but before I get started, I kind of wanted to go over some stuff with you guys just to make sure you guys are caught up. So I'm going to do a little bit of review on the type of stuff we've done so far, just to make sure everybody is, like I said, up on their material. So here we go. First thing, I'll call this a little bit of review, and then I'll tie this into our lecture of today. So the review is this. First things first. We've been doing limits, beating to death limits. When I take the limit as x approaches to, let's say, x squared minus 4 over x squared plus x minus 6. When it comes to limits, we basic on 3 different cases. There are 3 different cases of limits, and this is what we call a full limit here. What are the 3 cases of limits? So I'm going to write them over here. Cases for limits. Case number 1. When you take a limit, you plug in a number. Plug in the number. If you get a number, that is the limit. Basically, first rule of limits, plug in a number. It's called the substitution method, fancy in the book, but you basically plug in a number. If you get a number, you're done. That meant you actually had a function that had no problems. And so there's no real issues with actually taking the limit. The idea behind limit, it means I'm going to get very, very close to a number without actually being that number. But if the function has no problem, well, you're going to go ahead and be that number, and it's going to be the same answer. Case number 2. Plug a number. And if you get a number divided by 0. No, that's not, that's a special one. 5 divided by 0. When you divide by 0, you can't divide by 0 because it's violating the rule of mathematics. But here's the real deal. As you get very, very close to dividing by 0, you're going to blow up to either infinity or negative infinity. The way we defined full limits in this class is your limit has to go to a number. Infinity is not a number. It's an idea. It's the biggest number you can think of, plus 1, or negative infinity. The smallest number you can think of, minus 1. It's a number you never get to. So therefore, since it's not a number, we would say if you get a number divided by 0, then the answer is D, N, E. Now, what is my code for D and E? What does that stand for? Does not exist, no solution, however you want to write that, okay? Now, when you do the one-sided limits, you can blow up to infinity or down to infinity, but with a full limit, without little pluses and minuses behind it, we do not allow infinity answers, so it just does not exist. The case number 3, that's going to be your big case. First rule of limits, again, is plug in a number. And if you get 0 divided by 0, that's real special. That's that indeterminate form we talked about. Indeterminate form, because you can't tell what's going on here. So fishy divided by 0 doesn't exist. But 0 divided by 0, well, some things you cancel, because we're getting very, very close to 0. You know, 0.1 divided by 0.1, that cancels, you get 1. So is the answer does not exist? Is the answer 1? Well, the numerator is 0. Well, when you multiply 0 times anybody, the answer is going to be 0. So is the answer 0? Is the answer going to be 1? Is the answer going to be does not exist? Yes, sometimes. Okay, sometimes it's one of those or one of the other ones. I mean, I can give you all an example of each one of those cases. So you can't tell. So what you're supposed to do is then, and quote me on this one, do algebra. And what I mean by do algebra, typically you're going to factor and try to cancel something out. You're going to, key to it is going to be factoring. Simplify, cancel, factor, something or other. You got to cancel that denominator. The goal is 0, 0. Somebody's got to cancel. And if you can get that stuff to cancel, then do algebra, clean up, and then re-plug in the number and get your limit. So I threw an example up here for you guys. The limit as x approaches 2 of x squared minus 4 divided by x squared plus x minus 6. First rule of limits, what am I going to do? Plug it in. Now, remember, also, I'm trying to also teach you guys about writing this stuff up, because that's what you got to do for me on the test. As much as we love 21st century computer technology and make you guys do homework on the computers and stuff like that, fact of the matter is you're going to have to write this stuff up at the end of the day. How do I write this stuff up? On my test, I want to see some free response stuff here. How do I write this stuff up? When you plug in a number, you don't read write limit anymore. You literally just plug in a number. Our limit's going to 2. This will be 2 squared minus 4 over 2 squared plus 2 minus 6. 2 squared is 4, minus 4 is 0. 2 squared is 4, plus 2 is 6, minus 6 is 0. Yep, it's one of them 0 over 0 cases. But notice I didn't, when I plug in a number, I don't write limit anymore. So that tells me it's indeterminate form, which means I want to clean this guy up. So this will be equal to, and I'm going to clean it up. I keep writing limit until the point I plug in a number. Now, how do I clean this thing up? Well, I want to cancel something out. Well, you can only cancel through strict multiplication division, which means I want to factor this stuff. How does that famous x squared minus 4 factor? It's a difference of squares. How does it factor? X plus 2 times x minus 2. How does x squared plus x minus 6 factor? That factors into x squared. X squared is just x times x. 6, what times what is 6? That differs because of the minus sign by 1. Got to be 2 and 3. 2 times 3 is 6, but the difference is 1. Because it's a minus, they'll have opposite signs. Because the middle term is a plus, the bigger number is going to get the plus. So plus on the 6, minus on the 2. Now, strict multiplication division, what cancels? X minus 2 is canceled. So I'm going to clean that up. Keep writing the word limit. This is the proper etiquette of math here. Limit as x approaches 2 of x plus 2 divided by x plus 3. That's the cleaned up version of it. Now, re-plug in the number. And when I plug in the number, I don't write limit anymore. This will be 2 plus 2 over 2 plus 3. The answer is 4/5. That's my limit value. And that's the proper way of showing me the limit. Does that make sense? In the 0 over 0 case. Now, the other aspect of the review is, because a lot of you guys, when you're doing your Hawks review stuff and the lessons and stuff like that, you get a bunch of pictures. Well, you know, we've been doing the algebra stuff, but how do I actually analyze a picture? So, here's another example dealing with graphs. Here's your x-axis, here's your y-axis. Here's some kind of function. Here is the number 3. This is 5 on the y-axis. And here's a point up here. Here is 10. Let's say it's up there. All right, so I got a couple questions for you based on this graph. Based on this graph, question A, what is the limit as x approaches 3 of this f of x function? Fill in the blank. And then, part B, what is f of 3 equal to? Okay? The definition of a limit. I went through this guy with you guys last time, and the time before that. The definition of limit is this stuff here. This deals with that one-sided limit. Limit from below, limit from the left, and limit from the right. For a full limit to exist, the limit from below has got to equal the limit from above. They got to go to the same thing. So if I go after 3 from below, that'll be from the minus side. So that'll be limit as x approaches 3 from the left. where's my functional value going? 1 to 5. And if I approach the limit as x approaches 3 from the right, from the upper side, where's my functional value going towards? 5. So therefore, since it's going to the same thing, the answer is 5. It is that number. If I ever have this situation, limit from left doesn't equal the limit from right, then the limit answer does not exist. Okay? However, now this is a different question. What's f of 3 equal to? F of 3 is actually where is the dot, right at 3. Because the idea of limit is you're getting very, very close to 3, and you're trying to figure out where the functional value is going. Limit is, that's the limit. The functional value is what exactly is happening right at that point. Right at 3, where's the function at? That's where the dot's located. That's what we graphed, and what value is that? 10. It's the difference between a functional value and the limit. Does that make sense? So, let me give you another example. Let's give you the famous piecewise function-ish type stuff here. Officially, both of these are piecewise function. Here's your y-axis, here's your x-axis, and let's do this. Going to 3 again. This one is 2. This point is 6. Load in dot. I'm going to call them f of x because that's my famous name of the function there. So there's my function right there. Nice piecewise function. We would call this discontinuous. Yeah?
What did you say the closed dot was?
Closed dot is actually where the functional value is located at. That's the functional value. When you want to know what the functional value is, that's where your dot occurs at. So, based upon this one.
What do you mean by that?
The functional value. Well, if I ask you, and I'm going to in just a second, you'll see in a second, what exactly is f of 3? Where is f of 3 located at? And that's where the filled-in dot. Open circle means it's exclude. Filled-in circle means it includes. Include, exclude. Okay? So, part A. What is the limit as x approaches 3 from below of f of x? Part B. What is the limit as x approaches 3 from above of f of x? Part C. What is the limit as x approaches 3 of f of x? And the last thing, part D, what actually is f of 3? So I got 4 questions on this. Classic piecewise function. So, what is the limit as x approaches 3 from the left? There's 3 from the left. I'm going up to 3 on the left side of 3. Where is the functional value? As you plot the graph, where's the functional value going? 2. Answer's 2. What is the limit as x approaches 3 from the right? From the right, that means from above 3. Where is the functional value going? 6. Therefore, that concept, what is the limit as x approaches 3 of f of x? Does not exist. And the reason why it does not exist is because the limit from below left is going to 2, the limit from right is going to 3. I'm going to 6. It's not going to the same number. The only way a full limit exists, it's got to go to the same number. This is, again, from the graphing perspective. This is the definition of limit, for the limit to exist. But, now to answer your question, what exactly is f of 3? When you actually graph 3, at that point, where is the function graphed at? That's where the filled-in dot, that's where you plot the point. 3, the dot. Open circle means you exclude. The filled-in circle means exclude. So that 3, there's the function, and it is actually 6. F of 3 is 6. It's where the functional value is at. When you graph points, you plot points. It's where the point is plotted at. Does that make sense? Visual perspective of this stuff. All right. So to kind of fill you guys in on what we talked about last time. Last time we also talked about what we call the average rate of change. The average rate of change formula was equal to basically y2 minus y1 over x2 minus x1. But what we're dealing with here is a function. Again, some f of x. Here's your x-axis. Here's your y-axis. I'm going to plot 2 points. Here's x1, over here is x2. And if you plot these guys, this will be y1, this will be y2. And the average rate of change is the slope of the line that actually connects these 2 points that I just picked out, x1 and x2. But because this is defined by a function, y2 is also known as f of x2. y1 is going to be f of x1. So we get a little fancier formula for this. This would be f of x2 minus f of x1 over x2 minus x1. Okay? Now, so, using words to not throw you guys off with this stuff, this average rate of change is also known as the slope, because it's the slope formula. But this line of a particular function, when we connect 2 points, has a special name. It's called the slope of the secant line. Slope of the secant line. This line connecting 2 points on a graph is called a secant line. Okay? And so this slope, m, because that's our standard symbol for slope of the secant line, is basically, that's the symbolism for it. Okay? But now, what we're going to be talking about in section 2.1b here is about the idea of 2.2b is about the instantaneous rate of change. Talking about this concept. Here's the idea. All right, this is the average rate of change between 2 points. So I'm going to redraw this picture here. So draw my little line here. And let's see, here's the point right here. And I'm going to pick out a different point. And I'm going to pick out this point A right here. Here's my function again. Call this guy A. And I'm going to go move over a little bit, but instead, so this is like my x1. This is going to be my x2. But I'm going to call x2 A plus h, where this distance between these 2 points is actually an h distance. Here's the idea. This is an h distance between 2 points. Okay? Now, when we plot this guy, there's A. Put him over here. Here's your y coordinate. That'll be f of A. You plot this point right here. You put him over here. He's going to be f of A plus h. This is the new point, A plus h. It's A plus a little bit more. All right? Now, what we're going to do here is we're going to find the slope of the secant line between these two guys, the average rate of change between these two guys. And so the slope of this secant line between these two guys is going to be what? So this will be that slope of the secant line, slope secant here. And that's going to be f of, your y coordinates here, f of A plus h minus f of A divided by A plus h minus a. Change in y over the change in x. I'm using the exact same formula here. Does that make sense? But this one, the way we've written it up, you can clean it up a little bit. And so, if I clean it up, you'll notice the a minus a cancels for you. So you get a little formula called the slope of the secant line is going to be f of A plus h minus f of A all over h. And what you're doing here is you're finding the average slope between these 2 points. Here comes the idea. What we're going after is the instantaneous rate of change. So, this h is a distance between 2 points. What happens if I make this distance smaller and smaller? This will be like 1, and this will be like 2. But I want to pull this distance a little bit closer. So maybe we'll keep this guy at 1, but instead this is going to be this h is going to be 0.5. So this will be 1.5. So maybe this will be 1, and then make it 1.1, and 1 and 1.01. So what I'm going to do here is I'm going to take this point, and I'm going to pull him back on top of this other point. I'm going to make this h distance get smaller and smaller and smaller. To make this h distance get smaller and smaller and smaller, what we're going to do here is we're going to take the limit as h approaches 0, that distance, very, very small, of this f of A plus h minus f of a divided by h. And what you end up getting here is this. So here's my function right here, same function. So now we've got this point A, there's the point, and I made that point A plus h. I made him very, very close. And then remember, what we're trying to find is the slope of the line between these two guys. And when you pull that point right on top of each other, it's no longer what we call a secant line. When you have a line that just touches the graph at one spot and then moves on, that's got a fancy name. That's called the slope of the tangent line. So this becomes m subtangent. This is called a tangent line. Sure. This will be slope of a tangent line as we pull these things closer and closer to each other. Does that make sense? So you get this slope of a tangent line, and what this slope of the tangent line is, this is the instantaneous rate of change. Okay? The instantaneous rate of change of f of x at x equals a. So we have a formula here. And this instantaneous rate of change is also known as the derivative. So this slope of the tangent line, the instantaneous rate of the change, is also known as the derivative. It's f prime of a. The derivative of f of x at x equals a. The derivative of f of x at x equals a. And the symbol for that is f prime of a. This is the definition of derivative. It is this instantaneous rate of change. Okay? And this guy, remember, it's going to be a slope. This is the slope of the tangent line. So all these things mean the same thing. The tangent line of f of x at x equals a. It's going to be a numerical value. Instantaneous rate of change. Slope of the tangent line of f of x at x equals a. And then, the last thing we have here is, if I make a arbitrary, because now right now I've got to fix a, 45. I'm going to figure out the slope of the tangent line at 45, whatever a I choose. And we have a formula for it. But we can also make this arbitrary. So instead of picking the a point right now, we're just going to leave it as arbitrary x. So if I take the limit as h approaches 0 of f of x plus h minus f of x divided by h, this is going to give you, it's a formula for the slope of the tangent line, and I'll use those words. Formula for the slope of the tangent line of f of x. So instead of actually being a numerical value, it's going to be a functional value. And this functional value is called f prime of x, and that is called the derivative of f of x, called f prime of x, using what we call Newtonian notation. Sir Isaac Newton came up with this name. Okay? F prime of x. So again, what I'm talking about here is a little bit of theory, but wait, you have seen this stuff before. All throughout your high school career. All throughout your high school career. You have been dealing with something called, I bet you've seen this formula before, f of x plus h minus f of x all over x. We even threw a few problems at you guys even in this class. It's called the difference quotient. We even gave it a name called the difference quotient. But when you take this difference quotient, f of x plus h minus f of x all over h, and then take the limit as h approaches 0, that actually gives you what we call the derivative function, the rate of change function. okay? So here's a key word. When you hear the word calculate the rate of change, that typically means in a calculus class, you're going to be doing a derivative, okay? So, here we go. Getting the little notes out here. There they are. Now, if we look at this from a distance and time perspective here, okay? If I actually make the y-axis a distance axis, this is a distance, and the x-axis, we're going to make it a time axis. We're going to be graphing distance, okay? And so, when you find, we got a function, this will be d of t here. You've got some nice function here, d for distance. And you calculate two arbitrary points. Here's going to be t1, here's going to be t2 here. And you calculate, and this will be d1 for distance, this will be d2 for distance. So we're going to get that slope of the secant line, or the average rate of change here. Average rate of change of the distance between T1 and T2. Well, how do I calculate this average rate of change? Average rate of change is this slope. Keep jumping that at you. It's the change in y, that'll be d2 minus d1 over change in distance, excuse me, d1 minus d2 minus d1 over change in time. T2 minus T1. Change in distance over change in time. And to use the symbolism, well, in calculus, what is the symbol for change? So that would be delta D over delta T. Now, pay attention to units. If D is a distance, what is a distance measured in? Meters, feet, miles, kilometers, depending on metric system versus the English standard system, whatever, is some kind of a distance. Traditionally, what is time measured in? Again, it depends. Could be seconds, could be hours, could be minutes, could be years, right? So it's a change in distance over the change in time. Let's just go with some units you guys know. The change in distance, let's say it's miles, just to have a distance. Time is in hours. So this is miles, and that little divide mark means per, and miles per hour. So if you look at this from a distance perspective, what do the units miles per hour measure? Speed, or what we call velocity. You got it. So this change in distance over change in time is actually the velocity. Does that make sense? The speed, the velocity, because you can have direction on this thing. Okay? So here's the idea that we're coming up with. So there's a lot of even physics, and there's a lot of business applications of these units. But the key word is right here. You see that miles, that divide mark? That divide mark is the word per, and you're going to hear him a lot. This is a rate of change. Okay? So, here we go. In terms of this, all right, the whole purpose of section 2.2b is the instantaneous rate of change and interpreting graphs. See all my pictures. Determine the rate of change of an object at the instant when t equals a seconds. We need to analyze the average rate of change, delta d over delta t, for smaller and smaller values of change in time, making that limit go to zero stuff. That is, we want delta t to approach zero. In this lesson, we'll be able to use tables and introduce this concept. All right. So, first off, in the learn mode, hopefully on Hawks, you went and watched the learn mode before you came to class and listened and actually watched the little video and the little PowerPoint presentation thing here. All right. This is more of the theory questions. The average rate of change, delta D over delta T, is approaching the blank rate of change of the D with respect to T. Well, as delta T gets smaller and smaller and smaller, that's the key. Delta T is getting smaller and smaller and smaller. What you're finding here is the instantaneous rate of change. The instantaneous rate of change. And again, this The average rate of change is this classic change in distance over change in time, but as time gets smaller and smaller and smaller, instead of finding the average distance, average velocity, change in distance over change in time between 1 and 2 seconds, 1 and 1.5 seconds, 1 and 1.1 seconds, you want to know exactly what it is right at 1 second. That's that instantaneous. You made the distance go to 0. All right? The instantaneous rate of change with respect to time is called, well, you got the instantaneous, but here's the deal. We just talked about this a few seconds ago. It's the instantaneous. Now, what is distance divided by time also known as? Velocity. The rate of change is numerical interpretation of the delta y over delta x, which is the same as the blank of the line between 2 points. What is it? You know it. Slope. This is coming from the slope formula. Changing delta y over delta x. Changing y over change x. It's the slope formula. Number 4. The line that goes to 2 points on a graph is called the blank line. We have just 2 lines on a function. 2 points. What do we call that guy? The secant line. The line that goes to 2 points on a graph is called the secant line through the 2 points. The slope of this line equals delta y over delta x, which is the same as the blank rate of change. It's the same as the average rate of change as we're putting this stuff together. So you got 2 points. You use the average rate of change here. Between the 2 points introduced in the previous section. The line that touches the curve at exactly 1 point is called the blank line. There you go, tangent. Line to the curve at that point. So when you got 2 points, that's a secant line. When you make the line just go through 1 point, it's called a tangent line. Okay? The slope of a curve f of x at the point AB is exactly the slope of the blank line to the curve at that point. Okay? The slope of a curve of f of x at the point AB is exactly the slope of the, what kind of line was it? Tangent line to the curve at that point. This is also called the instantaneous rate of change, also known as derivative, but the word they were looking for here is the instantaneous rate of change. That instantaneous, that's that slope. The instantaneous rate of change is the slope of that tangent line. Numerically, the slope of the tangent line is given by the limit as, they use delta x, but here we go. The delta x approaches 0 of delta y over delta x, which is the same thing as this. Remember this formula? The limit as h approaches 0 of f of a plus h minus f of a all over h. And here it is. The derivative, and what was that symbol for derivative? F prime of x is the slope of the, being programmed here, tangent line at the point arbitrary x, f of x. This derivative, f prime, that's how we would call this, f prime of x, a little hash mark, prime. And that's the slope of the tangent line. For an input x equals a, for a given function f of x, blank is the height of the point, and blank is the slope of the curve of the point. Okay? We're trying to distinguish the two concepts here. If you're actually looking at a graph, here's a graph right here. You've got this point A. If I plot this point, this f of a right here, okay, this is actually how high the function is above the x-axis. So this would be the height, right? So f of a is the height of the point. Now, if I wanted to look at that tangent line going right through this point right here, the slope of that tangent line is also known as what? the derivative, f prime at a. So we're distinguishing between what f of a is, which is the y-coordinate, or how high the function is, versus f prime of a, which gives me what the slope of the tangent line going through that point of this function f of x is. All right. So, when you go to www.hawkstv.com and go to Essential Calculus, go through, we're in section 2.2b, and click on the little video there. They're going to give you a similar example of this one. And this is just an interpretation. We're not calculating anything. They gave you a function, great, and they just gave you a nice little statement here. F of x is equal to 4x cubed minus 3x squared plus 7x plus 1. Interpret the meaning of f of 5 equals 461. Well, this is a y-coordinate. This is f. This is not prime or anything like that. So this is your y-coordinate. So basically what we were discussing up here was this. What would f of 5 being 461 mean? This means the height of the function f of x, which is equal to 4x cubed minus 3x squared plus 7x plus 1 at x equals 5 is 461. When x is 5, you are 461 hash marks above the x-axis. This is possible. This tells you the height. But now, coming down here, interpret the meaning of f prime of 5 equals 277. Okay, well, basically there's three different concepts of this thing here. The first one is, all right, and then there's going to be three of them. Two of them are very similar here. The first one is the slope of the function called the curve, slope of the function curve at x equals 5 is 277. That slope of that function. When we talk about slope, we are talking about a linear thing here, but when we talk about the slope of a function, we are actually trying to be more specific about it. So we would use the word the slope of the tangent line at x equals 5 is 277. They were very, very close, but just you can call it the slope of the function if you want to, but it's really the slope of the tangent line. So if you graph that point and plot and graph a little tangent line there, that tangent line has a slope of 277. And the last one is, of course, number 3, is the, putting their words into it, instantaneous rate of change of f of x at x equals 5 is 277. So the instantaneous rate of change, the slope of the tangent line, slope of a function, they all mean the same thing. And the actually is referring to the derivative. All right, so turn back. Now, here's the idea behind this stuff. Well, first off, we're going to be tying all this stuff together. So, first one is this. We're trying to get some kind of visual stuff in this particular section. So you see lots of graphs on this. It says this. Number 1, in our practice. Find the slope of f of x equals -2 at the point 6, -2. Find the slope of f of x equals -2 at the point 6, -2. First thing I want to do is, I want to graph this thing. So here's my x-axis, here's my y-axis. My function is f of x. So f of x is the same thing as y equals negative 2. You know what a graph of y equals negative 2 looks like? Well, here's negative 1, here's negative 2, here's 1, here's negative 3 here. Y equals negative 2 is what kind of line? There it is right there. Y equals negative 2. Y equals, or f of x equals, a number is a horizontal line. Got a question for you. Okay? What is the slope? And this one put in there. Horizontal line. Let you know. Do you guys remember what the slope of a horizontal line is? Horizontal line has what kind of slope? Very good. Zero slope. So the answer is the slope equals 0. And it doesn't matter what point you're at. Here's a point, 6. And here's 6 right here. Here's the point, 6, negative 2. There's my point right there. It doesn't matter what point you pick on this thing. The slope at that point, or any point on this line, is going to be 0 because it's a horizontal line. So, all right. You guys looking a little worried to me here when I talking about slopes. Here you go. See this guy right here? Horizontal lines, what kind of slope do they have? 0. Vertical lines, what kind of slopes they have? Undefined. Slope does not exist. Undefined. What kind of slope is this one? Going from left to right. This is called a positive slope. And going from left to right, if you go down, it's called a negative slope. So here are your 4 slopes. 0, undefined, 0, here we go. 0, undefined, positive slope, and a negative slope. Okay? And you read a graph from left to right. Okay. Now on this one, I'm going to show you guys some tricks on this one. So on this problem, it says using a graphing utility, you're supposed to find the slope of f of x equals the natural log of 6x at the point of 2, 2.48. Round your answer off to the nearest hundred. Well, I'm going to show you how to cheat on this one because what they expect you to do is graph this guy. Hopefully you remember the old famous what the natural log of x graph looks like, but very few people do. When you plug in 1, natural log of 1 is 0, so it goes to 1. And the graph looks like this. It goes straight down and comes back and goes out this way. And here's the point 2, and the y-coordinate is 2.48. So there's my point right there that we're interested in. But I'm going to use my graphing calculator, so I'm going to go y equals, I'm going to type in my function. There it is. y1 equals the natural log of 6x. And I'm going to do this. I'm going to do a zoom 6. Zoom 6 is a negative 10 by 10, negative 10 by 10 screen. Now, I want you to understand your calculator. This thing gets very, very close to the x-axis here. The natural log of 6 actually shifts it up a little bit. But it'll be 1/6 over here. So my graph's a little bit off, so this will be 1/6. So 2 is somewhere over here. But yeah, there's my graph. But I want you to see that it gets very, very close to the x-axis and continues to go straight down. But the fact of the matter is, it gets so close to the x-axis, you can't distinguish it from the x-axis itself. But it is going straight down. But we're interested in this point 2.48. So I'm going to go zoom in on this thing. I'm going to kind of go over here and kind of plot where that point's at and zoom in on it right in there. So here's my graph right here. And I can clean up my window a little bit here and make it like -1 to 4 and -1 to 5. And this graph, just wanted you guys to see the little axis here. And I'm going to plot the point for you guys. Second, calculate value. X is 2, and there it is. There's my point right there. 2.4849, whatever. Now, what are they after in this problem? They want to know what the slope of this function is. That's the slope of the tangent line. Well, I'm going to grab myself a nice little sheet of paper here somewhere. I got tons of paper up here, but here's a good sheet, clean sheet right here. All right. So the tangent line would be something that looks just like that. And you want to figure out what that slope is. And so if you've got to estimate this thing, And see, there's my y coordinate here, here's my x coordinate. Rise over run. So this thing has a slope of about what? Well, it's kind of really tough to tell on the graphing calculator, right? Well, that's what you're expected to do. If you had grid paper, it would work better, but let me show you a little trick. I think the slope is around, well, basically, if you plot that point right there and kind of extend it on over here, it looks like you kind of rise about a half and run a 1, so it's around 0.5. But they want this thing rounded off to the nearest 100. I don't know how they're going to do that, except cheat. Second, calculate. Under calculate, where your really cool stuff is at. Value, this is your 0. That's, you can find the place where it crosses the x-axis. This is your minimum. If you got a graph, you can find where the smallest point is. Maximum is the biggest point. If you got two functions crossing, you can figure out the point of intersection. But you see that number 6 down there? That is dy over dx. Now what we're trying to do here is we're trying to find this instantaneous rate of change, the slope of the tangent line. Well, it's a slope. Did you guys remember this? Delta y over delta x. This was your formula for slope. You remember? But when you want the slope of the tangent line, you got to look at a little math history here. It doesn't matter if you were in Europe or in England, where this was developed, also in Germany. Leibniz came up with this stuff at the same time. Or delta, your Greek or your Latin or whatever. What does delta start with a letter? It doesn't matter if it's English or German or whatever. What does delta start with? D. And delta starts with D. So when you see dy over dx, that's a symbol for finding the slope of the tangent line. So I'm going to hit number 5 here. Number 6, excuse me. Number 6, I hit enter on it. And what point do we want to find the slope of the tangent line at? It was at x equals, what was it? 2. So I type in x equals 2. And it says dy over dx is equal to, so this dy over dx, which is that slope of the tangent line, is equal to 0.50000000 and something like 4, right? According to the calculator. So now I can get it out to that 100th spot, and I can tell you the answer for this problem is the slope of that tangent line is hundredths, that's tens, hundredths, is 0.50. That's what they're expecting you guys to do. They want to just show you guys kind of helpful hints on the calculator. Does that make sense? Dy over dx. It does mean derivative. It means the slope of the tangent line, too. All right. Take a look at this problem here. Again, this is that interpreting concept. Interpret the meaning. Question, yeah?
Sorry. Is it different in the A3 plus?
No. Can I mark?
Giving me.
Okay, so here we have the TI-83 plus. So we do second calculate derivative, and we want to put the point, okay, so first off, just double check. Y equals, and you graph it. We got a good picture here. Second, calculate the derivative, dy over dx. What x value do you want? 2. So if I type it in 2, I get 0.500004. It's written right down there. You hit the wrong button. No, that's all right. The difference between, good point, but the difference between the TI-83 and the TI-84 is one thing. Well, two couple things. This one has a newer operating system. You'll see that later in the class. But the other big deal is the 84, they threw more memory on the thing. So you got a lot more buttons to play with. But the buttons are still located in the same spot, and they do the exact same thing. This thing just has more memory on it. That's the upgrade system here. All right, this problem here. I want you guys to interpret the meaning of f of 3 equals 14 and f prime of 3 equals 7 and the function f of x equals 2 plus x squared. All right, so let's start with the easy one. What does f of 3 equal 14 mean? It means that f of x equaling 2 plus x squared has a height of 14 at x equals 3. One meaning and one meaning only. It's the height of the coordinate, the y coordinate. Height, in terms of graphing, is the y coordinate. Now, f prime of 3 equals 7. We're going to have pretty much 3 different kind of means here. And this means, the first one, we can say the slope of the curve at x equals 3 is 7. Number 2, word or there, the slope of the tangent line of f of x at x equals 3 is 7. Or, number 3, the instantaneous rate of change of f of x at x equals 3 is 7. And there'll be some more concepts of this. The derivative of f of x at x equals 3 is 7. That'll be next section. Okay? So we're going to try to type all these things in. Now, the next time when I meet you guys is I'm going to go through and do a classic limit definition derivative here, where we're actually going to use this function and show you that f prime of 3 is equal to 7. The slope of the tangent line is 7, but I'll do that for you in a limit definition next time. So that's what Mondays are going to be. So don't forget, 2.1a, 2.1b is on your quiz, and finish up your lessons. Don't hesitate. You lose points when you do. It's due on quiz on Saturday. Make sure you finish up all your lessons on Sunday. See you guys then.